Okay, welcome to a completely different topic, but this one's really fun. It's like combinatorics, and it's some stuff that you've already seen before in a previous math class, like in high school. You're like required to learn some of this, but we're going to go more in depth, and it's very useful. This is really like extra discrete for our discrete mathematics class, so this is lovely. I enjoy teaching it. So let's talk about how to count stuff. Let's try and remember how to count things, okay? So here are some fancy rules that you probably haven't heard defined in terms of sets before, but we love that, so we're going to do it. So let's talk about them. So let's talk about the product rule first, okay? So if you have A ways of doing one thing and B ways of doing another thing, then that means there are A times B ways of performing both, right? And that is pretty logical, right? So let's say that you have, I don't know, you go to your favorite ice cream place, and here are your options of ice cream and toppings. Let's say here is the set I of ice cream, so you can choose vanilla, you can choose chocolate, or strawberry. Let's just do the standard 3. So those are the ice creams that you can choose. And you could also, you have the option of, let's say, something easy like sprinkles. You can have either sprinkles or no sprinkles on your ice cream. So that's another set. So you can then ask the question, how many ways are there to get ice cream and a possibility of sprinkles? Well, there's 6 ways, right? Every option is a pair, right? Like maybe I want vanilla with sprinkles. That's my favorite. How many options are there like this? It's an ordered pair, right? So every option, bring in set theory into the mix, every option is in the set I cross S of all the ordered pairs. Take the first thing from here, take the second thing from here. There are 6 options total. Does that make sense? That's called the product rule. It's a very obvious thing, but it's useful when you're trying to count stuff. You can just multiply them together. So that means the size of the set, maybe you have n possibilities, right? The size of all those numbers of possibilities, all those Cartesian products together, is just multiply together the size of each individual set, each individual option, because you have like this many ways to do this thing and this many separate ways of doing this other thing. Okay? That's the idea. They don't come together or anything. So that's the product rule. The sum rule is also easy. If there are A ways of doing one thing and B ways of doing another thing, and you're not allowed to do both at the same time, like you have to pick one or the other, you have to pick from the A options or from the B options, then how many options total do you have now? Well, you have A plus B, don't you? I hope that makes enough sense. That's not really that bad, right? So if I have A, I could pick an option from A1 or A2 or AN all the way, all of these different sets with possibilities for me to do stuff, like activities or something. How many activities possible total are there? It's the sum of all their sizes. Assuming, though, that there's no overlap, like A2 and A1 don't share any values, because that would be cheating. Then this would be too many, right? You'd overcount. So as long as they don't overlap, at least, that's you can just add them, okay? That's the idea. So that's the sum rule. Again, a very logical thing, but let's talk about it in terms of sets, because why not? Finally, we have the bijection rule. This involves functions, right? So if there is a bijection from one set to another, that means that the 2 sets have the same cardinality. They have the same size, right? So for example, let's say that, let me come up with my example as I read this next bullet. So let S and T be 2 finite sets. Okay, if there is a bijection from S to T, then the size of S is equal to the size of T. This is the idea. So let me kind of draw it over here. Boop, 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 and boop, boop, boop. So if I have a function, like here is set S, here is set T, if I have a bijection, that means I have an invertible function that goes from one to the other, right? There's a way to go from S to T, and then there's also an inverse to go back from T to S, right? Every element of S hits exactly one element of T. There's a way to make it inverse. Does that make sense why they must be the same size? This cannot happen if there was anything more, because then it wouldn't either be 1 to 1 or it wouldn't be on to, right? There was nothing to hit. because of this, it's like, okay, yeah, every S has a T that it maps to, and vice versa if you flip the arrows around. So that's the bijection rule, okay? And then let's come up with a fun example for the sum rule, because why not? Let's just say that your option A is like, okay, I could go, it's summer break, I could go hiking or swimming. Those are my activities possible in set A. I can go outdoors and do cool stuff. Or I could stay inside. Here are my options B of, like, I don't know, I could watch a movie, it's too hot today. Or I could just eat dinner at some fancy restaurant. That is a separate set. Okay, so how many options total do I have of things to do? I could just do, well, size of A plus size of B. I have 4 total options. That's the sum rule. Okay, so product rule, sum rule, and bijection rule. Just given fancy terms and fancy explanations to things that you mostly understand, right? And so these work for finite sets. It gets a bit weird when you have infinite sets, right? Like the answer is infinity, infinity, and maybe this holds, but it doesn't make a lot of sense because infinity is equal to infinity. It gets a bit weird. So just consider these rules when you only have finite sets, and everything will work out. Let's keep going with that product rule, though, because it's going to get interesting. Okay? We're going to make some cool stuff out of that. So let's pretend, I don't know, my cool example is, it is the Cat Meme Olympics. So there are 15 contestants for cat memes, and we would like to give out to the 3 best cat memes the gold medal, the silver medal, and the bronze medal, of course. So we got to figure out how many different ways could this competition play out. How many different ways are there to give out gold and silver and bronze medals to potentially every possible candidate, right? So this is the way you're taught to think about it, right? There are 15 people who could win gold, right? You got to pick, like, okay, what are all the options? Here are all my cat memes. There's 15 of them. I need to give somebody the gold, I need to give somebody the bronze, somebody the silver, maybe in that order. I got to try all the possibilities. How many possibilities are there? So 15 people could get the gold. That makes sense, right? You have 15 options there. But then, after you've given someone the gold, there's only 14 people left to give the other 2, right? There's only 14 people now to take the silver medal if you give out gold first. Does that make sense? And that means once you've given out silver and gold, you've picked 2 people already. There's only 13 contestants left to get the bronze, potentially. That's how you count this. This is called a generalized product rule. You have 15 times 14 times 13 ways of giving out those medals to those 15 contestants. Does that make sense? That's called the generalized product rule. And it's mostly used to get up to speed about this concept of permutations, right? So how many ways are there to permute a set of things? All right. So using the generalized product rule, here are some, here's an idea. Here's what I want you to try. So consider these sets. You have a set of digits, a set of lowercase letters, and a set of special characters. And I would like you to come up with the number of passwords that satisfy the given constraints, these constraints here. So the password must be size 5, 6, or 7. So there must be 5, 6, or 7 characters. The characters can be special characters, digits, or letters, but the first character must not be a letter. It can only be a digit or a special character. So with that in mind, see if you can come up with the number of passwords that satisfy those constraints. Okay? So, how many are there? I think the easiest way to break it down is to come up with the sets of all the length 5 passwords and the length 6 passwords, because they kind of are formulated differently, and all the length 7 passwords. And then the answer is, because there are no overlapping passwords of different lengths, right? The answer, if only I can spell answer, is going to be the size of that set plus the size of this set, all those passwords, plus the size of all these passwords. Okay? So that's where we're going with this. Let me show you how to come up with the size of the length 5 set. The number of all the passwords of length 5 that satisfy these constraints. The rest of these constraints, that is. And this is kind of the way I want you to do it if you didn't get it this way. So the first character can't be a letter, so it's forced to be either a digit or a special character. Let's call this let's call this set D, let's call this set S, let's call this set L. So it's going to be, for your first character, what options do you have? You have sum rule. You can choose either a digit, so that many, or you can choose a special character, so that many, where D is for the digit set and S is for the special character set. So this is the total possible characters that you could choose for your first character in a length 5 password, because it must be something other than a letter. So that's like that. And then the rest of your characters, product rule now, the rest of your characters can be anything. It could be a digit, a letter, or a special character. And you have 4 left, because we just picked the first one. So generalized product rule. Do you see how these are all working together? So the last 4 of your characters could be either a digit, or a letter, or a special character, and you can have 4 more of those. So these are your options. Take 4 of those arbitrary options, and remember your first character could only be one of those. So that is the size of all the passwords of length 5. Does that make sense? So this is the first character, and this is the other 4 characters. There are 4 chars. And then like length 6, it should be very similar, right? Like all the length 6 passwords is equal to, well, you got to pick again a digit or a special character. Those are your options. And then after that, you could pick either a digit or a letter or a special character. And because your password must be length 6 for this set, the size is going to be 5 here. You take this to the 5th power because you need 5 extra characters after the first one. So I think you can do that for length 7 and actually calculate this, but that is the setup. Okay? That's how I want you to think about it. Okay, so that's one thing. Another option, try this one. This is fun. So normal license plates in California, they go digit, 3 letters, and then 3 digits. And the letters are all capital, of course. So how many of these default license plate numbers are possible if no digit or letter appears more than once? Okay, so you cannot have, like you can't have 5AAA, 555. Okay, you can't do that. It's got to be instead like 5ABC, 678. You can't have any digits or letters appearing more than once. Okay, so that one's not good. That one's okay. So see if you can count the number of possible license plates of that form. Okay. And here's how I want you to think about it with the generalized product rule. So at the very start, you have to pick a digit, right? You have to pick a digit first. There are 0, 1, 2, all the way to 9 digits, so that's 10 possible, right? And then there's also, the second you have to pick a letter, there's A, B, all the way to Z. There's 26 of those, right? So let's remember that. But the first thing that we need to pick is a digit, and we haven't used any yet, so we have 10 options. Okay? Then I need to pick, so that's my digit, and then the next thing that I need to pick is a letter. Next thing needs to be a letter, and I don't want to repeat anything, but I haven't picked any letters yet, so I have 26 options for the next letter. Okay? That's the idea. That's the next letter. And then, well, I have to pick another letter, but it can't be one that I picked already. I've already picked a single letter, so if I picked A, I can't pick A anymore. If I picked B, I can't pick B anymore. So I have 25 options left for that second letter. Does that make sense? That's how you think about this. And for your third letter, that means you've picked 2 already. That means there's only 24 left in the alphabet to choose from if you don't want repeats. And then I think you get the idea. I need 3 digits. I've already picked a digit, so there's only 9 possibilities left to choose from. I'm not sure which one I picked, but there are 9 left no matter what, right? And then after I've picked 2, I need this other digit. There are only 8 left. And for my final digit, I've picked 1, 2, 3 already, so there's only 7 left to choose from that haven't been seen before. So I have 7 options left, and this is the answer, whatever this number is. That's how many license plates there are if no digit or letter appears more than once with this style. Okay? Did you get that? So yeah, this is just fancy counting stuff. These are fun little problems to me, at least. So let's keep going in this style. Let's actually talk about permutations now. Let's see where we're going. Yeah, plenty of time. So a permutation now is a sequence that contains every element of a finite set exactly once. Okay? That's the idea. So a permutation, a single permutation, and this is, I'm going to teach you permutation and R permutation. So a permutation without the letter R in it looks like this. Say here's your set A, like it's the set of numbers 1, 2, 3, 4, and then a permutation of A of this set is a sequence that contains each element exactly once. So here is a possible permutation of A. 2, 1, 3, 4. Okay? So that's A itself. This is a permutation of the elements of A. That's what that is. And here's another permutation. Like, maybe I can do 3, 1, 2, 4. Okay, so those are permutations. And there are n factorial different permutations, right? What are all the different ways that you could arrange the elements of A? Well, we have, it's going to be 4 factorial. Because, watch, I have 4 to pick for the first element, 4 possibilities, I can pick any of them, and then there's 3 left for the second element, 2 left for the third element, and 1 left for that fourth element. Isn't that nice? 4 factorial. So there are n factorial different permutations when n is the size of the set. That is a nice result. Next definition gets a bit fancier. Let's talk about an R permutation, okay? An R permutation of a set is a sequence of R items with no repetitions, all from the same set. So it's not, you don't have to pick out everybody, just a couple, okay? So let me show this to you. The sequence 1, 4 is a 2 permutation, because R is really a number. So 1, 4 is a 2 permutation of A. I take one thing out of A, and I take another thing out of A. It's just take a couple things without any repetitions from the same set, okay? So that's a 2 permutation of A. So are, like, just take 2 elements. So are like 2, 3. So is 4, 3. 1, 2. Those are a bunch of 2 permutations of the set A. So take 2 things. And you can also ask the question, hey, how many 2 permutations are there of the set A? How many different how many different sequences of size 2 where you take elements out of A are there? That's the idea. And so we're asking the question, how many 2 permutations are there of a set with 4 elements? Yeah? You can generalize that to say, how many R permutations are there from a set with n elements? So it's like PNR is what it looks like. So we want to ask the question, hey, what is P42? Because A has 4 elements, and I want to pick 2 things out. How many different ways are there to do that? The answer is going to be 4 times 3, right? Because, again, I can pick anything for the first. I have 4 options. And then I have 3 options left for the second element. So it's really 4 times 3. That is the answer. That's how many 2 permutations are there in the set A. And the general formula is this. Okay? Let me prove that to you. It's n factorial over n minus r factorial. Okay? And we just discovered this on our own using the generalized product rule, but I promise that this formula always works as well, because it's going to be 4 factorial, 4 times 3 times 2 times 1, over n minus r factorial, which is, so 4 minus 2 factorial, so that's 2 factorial, is 2 times 1. So these all cancel, and it's left with 4 times 3. Hey, it does work. Okay? So this is the way to count R permutations of a set. Okay? So the number of normal permutations is just, okay, PNN. You're counting all the different ways you could take n elements of the n element set. But you don't have to take all of them. You can make these smaller sequences. Okay? So, yeah, the moral of this story is that a permutation of a set, regardless of the size, is just a tuple, because we care about the order. It's a sequence. So 2 then 3, 4 then 3, 1 then 2, in that order. So it's got to be a tuple, because order matters there. Can't be a set. Okay? So that's permutations. And now let's talk about a fun example. All right, so this is a fun one. South Africa, their lottery was investigated for like fraud after they drew the balls 5, 6, 7, 8, 9, and 10 in that order. Okay, where there were 50 balls that you could draw. Those are your possibilities. Oh man, they picked that weird looking order, which is not very likely, right? So let's see how likely that was, or how unlikely it was. So like a normal lottery draw would have been, okay, pick some numbers from some balls, like 50, you could pick 42, then 1, then 8, then 7, then 23. Look at all these options. But they got the permutation, 5, 6, 7, 8, 9, and 10. Crazy. So how unlikely was that? Technically, with enough lotteries, you'll get weird looking stuff like this, but how unlikely was it? So here are the odds. If you have 50 balls total, it was, all right, how many different ways? It was one way out of how many different ways are there to permute 6 balls, right? This is the number to pick. Out of 50 total, okay? Number of lottery. I think the word is balls, right? You're drawing them out of some like weird ball popper machine. That's the idea. So how many ways are there to do that? Well, it's going to be 50 ways for the first ball, then 49, then 48, then 47, 6, and 5. So that is 1 in 11.5-ish billion chance. So technically, if you ran a lot of lotteries, you'd eventually get these odds, and this would happen naturally, but it's so unlikely that they had to look into it. Isn't that cool? So that is combinations in real life, or counting in real life. Combinatorics is the right word, sorry. All right, question for you now. Let's talk about this, another example. There's a lot of ways to use permutations as an idea. So let's pretend that you're at a wedding and there's 10 people, and like you're the photographer maybe, and there's 10 people in the wedding party and they're lining up in a row for a photograph. So you got to take a picture of everybody, all the important people, and here's the question. How many ways are there for you to line up the 10 people if the groom must be immediately left of the bride? So we want the groom on the left and the bride right next to the groom on the right. Yeah? That's the goal. It gets everybody's good side. So here is like, I don't know, here's the picture, here's all your people. But you are forced to, doesn't matter where you put them, but the bride and the groom better be in this order. It better be groom and then bride right next to them. And then you got more, all the rest of your 10 people. Okay? So what is the ordering? How many ways are there to do this? The bride and the groom can be anywhere, but they have to be right next to each other in this order. So think of it that way, okay? So, and there's more people, right? Here is the secret. Here's how you do it if you didn't figure it out. The way that you consider this is, well, the bride and the groom have to be in this exact arrangement. They must move as one. Does that make sense? So you can just count them as one object. Just count as a single person, kind of. One person that you can move, because they're like a set. They come together, right? If you do that, then you have 9 people to move, technically. Does that make sense? 9 people to order. And so there are 9 places to put the bride and the groom, right? It could be in between anybody. There are 9 options for who comes first. Then, like, options for who comes first, where who is in quotes because it could be multiple people, right? Who comes first? Because we're treating the groom and the bride as the same person. And then 8 left, then 7 options for who comes third, 6, all the way to 1. Okay? And that is 9 factorial. That's how you think about this problem. Does that make sense? Did you get it? So that is the goal. You can just treat this fixed object as one person. Even though there's 10 people, pretend there's 9 really. That's how you do it. So yeah, that's a fun example, I think. Let's keep on trucking. Counting subsets. So here's a set A, 1, 2, 3, 4, 5. You might ask the question, how many subsets of A are there? Right? And the answer is, it's going to be, well, the size of the power set, of course, right? That's the question. How many elements are there? How many, like, subsets of A? What's the power set of A? Remember, it's you got the empty set, you got the set with just 1 in it, the set with just 2 in it, all these options, until you also have the whole thing, right? 1, 2, 3, 4, 5. Those are all the sets in the power set of A. How many are there? There are 2 to the 5, okay? That's the idea, because you could either think of it this way: if you're creating a subset, you got, well, how many options? Do you include this one or do not? 2 options for that. Do you include this one in your subset or not? 2 options for that. That's why it's 2 to the 5. There are that many subsets total. You might ask, then, how many subsets of size 1 are there? Right? How many subsets of this set of size 1 are there? There's 5, right? Take the 1, take the 2, take the 3 by itself, the 4, the 5. That's how many subsets of size 1 there are of this set A. What about how many subsets of size 5 are there? It's just 1, right? Because it's just, you can just have A itself. That's the biggest set originally. There's only one way to take them all. It's to just take them all, right? There's only one set of size 5 in the power set. That's the original set itself, okay? And then you can ask about things in between. That's where it gets tricky. So what about all the sets of size 3 from the power set of A? How many subsets have size 3? You got your 1, 2, 3, your 1, 2, 4, your 1, 2, 5, your 1, 3, 4, I guess. That looks hard. How do we do that? So let's talk about how to do it. There is a way. Okay, here's the trick. Let's use these concrete values. Like, we have a size 5 set. We want to count the number of size 3 subsets of A. This is an important idea. We could start with permutations, right? Because permutations kind of gets us to the right spot. If we ask for how many 3 permutations are there of a size 5 set, it tells you how many permutations of length 3 there are, right? Like, you can pick 1, 4, 5. You could also, though, pick 1, 5, 4. That's also an equally valid permutation that's counted in all of these. And this is a bit of an issue, right? Because we end up overcounting. Because really, if you turn these both into sets, they're the same set. The order doesn't matter in a set, right? So if we're counting subsets, we're going to overcount if we use permutations like this. But this is most of what we want, right? We're giving all the options. We're just sometimes overcounting. So we kind of have to get rid of those duplicates. So let's talk about how to do that, okay? So for example, if we want to count the subset 1, 2, 3 just once, but we ask for the number of 3 permutations, we're going to get all of these, right? These are a bunch of 3 permutations. They're all separate 3 permutations of that set A, and they all stand in for 1, 2, 3, don't they? They're just some arrangement of 1, 2, and 3, right? Those are all the options for those permutations, right? But they all are going to stand for 1, 2, 3. We're overcounting this 6 times, right? So the order of that size 3 subset does not matter. So we end up counting each subset. Just think of every possible subset. This arrangement always happens. You count every one of them 3 factorial times, because that's how many ways there are to arrange 3 things. You overcount 6 times. We'd like to count each of those just once instead of 6 times. So that's the trick. If you want the count of how many subsets of size 3, well, take the permutations first, but divide away by how many duplicates you know you're going to get each time. Divide by the factorial of that subset size. Okay? So the final count, therefore, must be the number of 3 permutations of a size 5 set over the number of different ways that you could have arranged a single permutation of a subset of that size that we care about. So it's 3 factorial ways to arrange 1, 2, and 3. Yeah? That's the goal. That's what we divide by. And so this is going to be 5 times 4 times 3 over 3 times 2 times 1. Okay, so those cancel, and it looks like we're left with 10. There are exactly 10 different subsets of size 3 of a length 5 set. That's the answer. Okay? That's fun, I think. And so the generic term for this is called a combination, okay? You've probably seen this syntax before. That's what we're asking for. So you can also ask about it as CNR, okay? That's the number of R subsets or R combinations, that's another word for it, in a set with n elements. Okay, so let's put combinations in bold because that's a new word. Whee. Okay. That's how you do it. So how many? We were asking for how many elements are in a R-sized subset out of a set with n elements in it. Okay, so we're asking for, in our example, I don't know, C of size 5 set, but we want 3 things. Okay, another symbol for that is this 5 up here and 3 down here between parentheses. That is equal to 10, like we just did. We calculated it this way. This is the full formula, and this is how it breaks down. Okay, we just discovered that on our own. And the syntax for this, if you write it like this, it's called I don't know, it's combination notation, let's say, but this is how you pronounce it. It's the word choose. C for choose, kind of. You say n choose R. Okay, so you got n things, choose R of them. Count all the subsets. Okay, that's the notation that I will be using a lot. Okay, so that's how you count the number of R subsets in a set with n elements. CNR, n choose R, and this is the number, which simplifies to this. Okay, so again, no repetitions are allowed because we're trying to count the number of subsets. Okay, and so just like a permutation is a tuple of things because order mattered, a combination, a subset, is just a set. The orders don't matter. Okay, that's the idea. So you've definitely learned this before. I was forced to learn this in high school. I assume they still teach it. Back when your math teacher was saying, like, okay, we're counting things and the order doesn't matter. They kept saying that, right? And then they moved on. They didn't say any more. It's like, okay, yeah, order doesn't matter. That's fine. They didn't really talk to you much more about that. And the reason was because they didn't want to get into set theory. That's why. Okay? So now you're ready to learn about everything. That is combinations. And you can use them for very interesting ideas to represent those things, to count some interesting topics. Okay, so here is a set S. It's got 6 elements. How many subsets of S have either 2 or 3 elements? Okay, so see if you can figure that one out. Well, I think the easiest way to count this, the number of subsets having either 2 or 3 elements, is to first separately find or separately count, let's say. Count the size 2 subsets, and then also count the size 3 subsets. That's the idea. And then just add them together. So 6 choose 2 plus 6 choose 3. How many ways are there out of 6 things to choose 2 elements? How many ways are there to make subsets of size 3? And so that answer is what we get. Okay, so it's going to be 6 choose 2 is going to look like this. It's always n factorial over r factorial times n minus r factorial, or pnr over r factorial. Okay, so it's that one's easier. So how many ways are there to permute 2 elements out of a size 6 set? Well, it's 6 times 5. 6 options for the first thing, 5 options for the second thing. And we don't want to overcount. How many different ways are there to permute any subset of size 2, because that's how many times it's going to appear in the permutations. We want to divide by that. That's 2 factorial, so 2 times 1. Okay, so we do that plus, and then we do 6 choose 3. So that's going to be 6 times 5 times 4 over 3 times 2 times 1, 3 factorial, right? That's the idea. So that is the number. I won't calculate it, but that is the answer. Okay, did you get that? You can get even fancier with your permutations, though, because it doesn't just have to be coming from a set, because sets never had duplicates. You can have duplicates. You can have repetitions in real life when we need a way of talking about those things, okay? So a permutation with repetition is when you have a set of items that you want to figure out the order of, but some of those items are identical to others. So, for example, you want to figure out all the different ways there are to permute the letters of the word lol. Yeah? If you did it normally, right? If you did it normally, you would think like these two L's are separate characters, right? You'd be like, okay, I'd make the set L1, then O, and L2 when I try to permute all of them. But if you were to do that and to come up with an answer, you'd be saying things like, okay, L1, then O, then L2 is not equal to the order of L2 first, then O, then L1. But it's still LOL. Do you see that? It's really just LOL and LOL again, and they should be equal. So we need to do something about that. We want to consider all the orders of these letters where, like, if we permute, we don't care which L we take. If it looks the same, it should be counted as the same thing. We don't want to overcount anything, okay? That means that some permutations are the same as others, and we don't want to double count them, okay? So let me figure out the right answer to this. It looks like you can do normal lol, or you could do LLO, or you can do OLL, right? Those are your options. And here's kind of how you pick, okay? Here's kind of how you pick. It's going to look like this. Whee. So I want you to think of it this way. You need to permute the characters of a word. That means you have 3 slots to fill in, 1, 2, and 3. You can put an L here, you can put an O here. That's the idea. So the question is, what are my options? Where could I put my L's? Okay? Let's pick where to put the L's first. That's the secret. And the question is, how many ways are there to pick 2 options for each of those L's? Okay? Well, the answer is 3 choose 2. There are 3 choose 2 spots for L's. And this will make more sense with the next example too. But here's the idea. It's like, okay, I have 3 options. I need to pick 2 of them to put my L's, and the order doesn't matter, so combinations. Okay? Maybe it's saying, okay, here's a way you could put 2 L's there, you could put 2 L's here, or you could put 2 L's here. There are 3 choose 2 options for your L's. And then the last option must have that O. There's nothing left. It's just 3 choose 2 times 1 as the answer. Okay? That's the idea. And there's 1 spot left for an O. Let's give myself some more room here, I guess. 1 spot left for the O. So that's the idea. Let me try and break that down again a bit slower. So let's pretend that we want to count the ways of permuting all the letters in Beyonce. So again, let's find all the duplicates. You have 2 E's. And so the idea is we would like to first find spots for all of the E's. It's a 7-letter word. So here are all the slots that we could fill. 1, 2, 3, 4, 5, 6, and 7. And so your first thing to do, your first thing to solve is there are 7 locations. You need to figure out where you could put the E's. Place the E's first, where order doesn't matter. Like the first E and the second E is the same as putting the second E here and then the first E here. That's the same thing, right? So it's a subset that we're counting. What are all the different numbers? Like, I need to pick 2 of these numbers to put an E at, essentially. What are all the different ways that I could do that? I have 7 options. I want to pick 2 of these indices to put an E at. So it's 7 choose 2 options for those E's. Like maybe I pick this one and this one. Okay? Once I've done that, once I've picked where the E's goes, where the E's go, I have, regardless of where I put the E's, I have 5 options left for the rest of the characters, the ones that don't have repetitions. Does that make sense? That's how you count this. There are 5 locations left for everything else, and there are 5 factorial ways of permuting the rest of those characters that don't have duplicates. So it's pick the locations for the duplicates, then worry about the rest of the characters. If you just multiplied those together, the ways of counting all the way, the count for all the ways to permute those letters is 7, choose 2. So find the indices of those duplicates first, using combinations, because we don't care about duplicates. We don't care about, like every E should be considered to be the same. We're counting subsets. And then we have 5 factorial options left. Okay? So that's how you permute all the letters of a word, where you have repetitions. All right. So this, like, the idea makes sense, and we can generalize that. There is a nice little formula for each word scrambling kind of problem with these kinds of repetitions. So let's do a hard word like Mississippi. Let's try to scramble all the letters of Mississippi, and that will help us generalize this idea, okay? To come up with a nice formula that you can just not look at ever again, okay? So Mississippi has 11 characters, I counted, and so that means we have 11 slots to fill. 5, 6, 7, 8, 9, 10, 11. Okay, and you can pick whatever letter first you wanted to do, but let's pick a big one, like let's try and permute all the S's first. So let's try and place the S's in 4 of the different slots. Okay, so the idea is, because all the S's are the same character, what we want to do is just pick 4 arbitrary indices, a subset of these potential 11 indices, to put our S's at. Okay? How many ways are there to pick a spot for each of our 4 S's? That comes down to asking, all right, how many different subsets are there of 1 through 11? Because that will give me the index at which to place that S. So the answer is 11, choose 4. I have 11 options. I have 4 things to place. I need a subset of size 4 out of these indices to place my S's at, and that's where they can go. Like, I'll put an S there, S there, S here. Okay? So there are 4 S's to place. Okay? And after that, after you've done that, you've placed 4 characters somewhere. That means there are 7 free spots left to place more characters. Does that make sense? So let's say we want to put the I's somewhere next. There are 4 I's also. There are 7 slots left, so 7 indices where we could put those I's. We need to pick 4 of those indices, because we have 4 I's to place. So 7, choose 4, we multiply it by. Okay, 4 I's. And then we have 2 P's left, and there are, let's say we put some I's there, I there, I there, I there. We have 3 slots left, regardless of where they are, there's still 3. There's always 3 slots left after we place those to put our 2 P's. So there's 3 slots left. I need to pick 2 of them, choose 2 of them, please. Order doesn't matter, to put each of my P's. 2 P's. And then finally, once I place my P's, there's only an M left, and there's only 1 slot left for it. Regardless of where it is, there's only 1 slot left. I'm forced to place my M there. There's only 1 place left. 1 slot left for that M character. Okay? And so this is kind of the idea. It's like, for all the repetition stuff, you do how many things originally are there, how many duplicates of that particular character are there, and then you keep multiplying that by another combination where how many things are left, how many things are duplicates for those letters now, then again, how many things are left, how many duplicates do we need to place? That's the kind of idea. And so there's a nice formula in your book where instead of saying Mississippi, you say, like, pretend that M is the letter 1, M is the number 1, I is the character 2, and so on and so forth. And then you try and count the number of distinct sequences with certain numbers of 1s and 2s and K's in that order. Because then you'll have a bunch of, instead of characters, you have the numbers 1 through how many different characters there are. And because of that, that gives us a nice little formula. Okay, there are, it looks like this. And let's go from that to it. Let's discover this formula together, okay? You don't really have to go through these characters to numbers, but that just generalizes the whole thing from words to like a general problem though. So, yeah, let's do this. Remember this formula. So what's 11 choose 4? One way to do it is it is 11 factorial over 4 factorial times 11 minus 4 factorial. So 7 factorial? Yeah. This is what it looks like. This one is 11 factorial over 4 factorial times 7 factorial. And then we're multiplying it by this, which is following the pattern, 7 factorial over 4 factorial times 3 factorial. And this is multiplied by this, which is 3 factorial over 2 factorial times 2 minus 1 factorial, which is 1 factorial. And then this one is technically one slot left for the m. Well, how many elements are there to place? 1. What's 1 factorial? And then you do that. How many different, as 1 choose 1 essentially, right? Over 1 factorial times 0 factorial. This is equal to 1 choose 1 in parentheses. Okay? So that's kind of what you're doing there too. So you can turn this all into a bunch of combinations, and this is the formula that you get. And look at what cancels. Bam, bam, bam. 0 factorial is defined to be 1, so you can just let that go away. But look at the nice formula. It's the original number at 11 characters, 11 factorial over all the duplicates, the counts of all those duplicates. You had 4 duplicates of the S's, 4 duplicates of the I's, 2 duplicates of the P's, and 1 duplicate of the M. There's only 1 M. So there's 1 factorial in that spot. Isn't that cool? So there's a nice formula for that you don't ever have to look at it again, but you just can immediately get the answer by doing a bunch of factorials. Okay, but this is the rationale behind it. Okay, doing all these combinations. So whichever one makes sense for you, please do that and try this one. So how many ways are there to permute the letters in the word college? So again, like think of it as this is a size 7 word, so there's 7 slots to fill, and we have some duplicates. We have 2 L's and 2 E's. So the first thing we need to do is fill in those duplicates. Like, okay, which indices get the L's? 7 possibilities, 2 L's. Then there's 5 left, and I need to put the E's. 5 possibilities, 2 E's to place. And then we have 1, 2, 3 characters left to go in the remaining slots in any order because there's no duplicates among them, so it's just 3 factorial at that point. And so you can do it that way, or this is going to be equal to doing it this formula way. You can just read it off. Well, there are 7 slots, 7 factorial over how many duplicates are there of each letter. So you have, let's count the L's, 2 factorial. How many E's are there? 2 factorial. And just put a factorial after that count. And then you have 1 C, 1 O, and 1 G. So how many different ones of those are there? Put a factorial next to them. There's 1 factorial times 1 factorial times 1 factorial. And those all cancel out, of course. So that is another way to get at the answer. So whichever way you like, use that, but those are your options. All right. So that's permutations of things with duplicates. All right, and you can actually give a name to that. You can think of, instead of having to use a bunch of words to teach this, I could have said the word multiset, okay? This is a more general term. So a multiset is a collection that can have duplicates of the same thing. So again, it's going to be a set, so that the order doesn't matter in which you write these things, but the count does matter. So each same item we say is indistinguishable, okay? So this is a multiset. You use the set notation, but you can have duplicates, and they count as duplicates, okay? The order of each of these numbers doesn't matter, just like for every set, but it's not equal to this. If it were a set, it would be equal to that, right? But we're doing stuff with multisets now. There really are 4 separate 7s, but we consider those 7s to be indistinguishable, okay? That's the idea. So multisets come up a lot because that just happens a lot in life. Like, here are all the bills in your wallet, for example. That's completely different from the set that it would shrink down into, right? We want to count how much money we really have. We don't want all of our 20s to vanish, right? So multisets do come up in a lot of real-life examples, and so we need some theory for them. And so here's the kind of thing that we'd like to count with a multiset. Here's a standard problem that you might have. Given an infinite supply of things, figure out how to fill a basket. So here's our basket. Easter's coming up, so that's perfect. Whee. So here's your little basket. Figure out how to fill it with n items from m different varieties. Okay? So for example, which we'll have on the next slide, let's pretend that our basket can hold 10 dogs. So we're picking up 10 puppies from the shelter for some reason, because why not? And there are 4 different breeds to choose from. Okay? And we're going to consider dogs of the same breed to be indistinguishable. So maybe, I don't know, you have your golden retrievers. You can pick from those. That's one of your breeds. You have labs to pick from. You have chihuahuas to pick from. And then, I don't know, I don't really know many dog breeds. Maybe you have a poodle to pick from. Those are your 4 options. Okay? And then you need to pick 10 dogs of each of these breeds. Okay? You have 4 breeds to choose from, 10 dogs total. You could pick 10 golden retrievers if you wanted to, or you could pick some golden retrievers, some labs, some chihuahuas, some poodles, as long as it sums up to 10. That's the idea. So that's standard. Like, you can see how there's a multiset involved, right? And this is a problem that comes up a lot. So let's learn how to count these things. What are all the possibilities? How many possibilities are there of choosing 10 dogs exactly from 4 different breeds? Okay, where we have an infinite supply of puppies. And that's a nice world to live in. So here's the way to do it. Okay, so remember our problem. We had 10 dogs to choose, and we had 4 breeds to choose from. Okay? Here's the secret to counting the possible multisets that could come up. Okay? The trick is to imagine each potential outcome, each potential basket, as a binary string. Each potential multiset is a binary string. And I'll show you how this works for the dogs example. So let's say we pick 3 golden retrievers. You can turn every possibility into a binary string of 1s and 0s in this way. Let's say we pick 3 golden retrievers, so it's 1, 1, 1. And then I'm going to pick 4 labs. 1, 2, 3, 4 labs. And I don't know, how many do I have left? I have 7, so I have 3 left. Let's say I want 3 chihuahuas and no poodles. Okay? Let's turn this into a binary string. So here are our 3 golden retrievers. I'll put a 0. And then here are our 4 labs. Here, I'll put another 0. Here are our 3 chihuahuas. I'll put a 0. And then here, I don't put anything because I don't have any more dogs to pick out of the poodle basket and place in my own. Okay? You can turn every option into a binary string. There's nothing there. Where the 1 is how many things you're taking of each breed, for example, of each category. And then you have 0s as a separator to say, here are all the things of this one thing, this one category. Here is the separator before I talk about how many things I want of the next category. Do you see how every possibility, every possible basket can be turned into, regardless of the counts of all of the dogs, a separate binary string? Because then we can start counting binary strings instead, and those are a bit easier, okay? So that's going to turn into this fancy formula. The number of ways to select n objects from a set of m varieties is n plus m minus 1, choose m minus 1. Let me show that to you, okay? So this is the idea. This is what this is trying to say. It's n plus m minus 1, choose m minus 1. What does that even mean? So for our case, we're trying to calculate what? We had 10 dogs and 4 breeds, so n was, in our example, 10, and m was 4. we're trying to calculate n plus m, so 14 minus 1, so that's 13. Choose m minus 1, which is 3. Okay, that's the number we're trying to calculate. That's apparently how many different binary strings there are. And, okay, 13 is, if you look at this and you count, 13 is, oh man, the number of characters in the binary string. And 3 is, what are there 3 of? It's the zeros. So you're forced to have 10 ones, and then the only thing that you can vary in your basket is where you put the zeros to say how much of which dogs you need. Does that make sense? So this formula means, if you think about it in terms of binary strings, you're trying to count all of the places you could put those zeros, because that gives you a different type of basket. Picking where you want the zeros to go in the string. You're forced to have n ones, of course, because you're taking n things. The only thing that you get to choose is which kinds of those things. So where do you separate? When do I stop picking from the golden retrievers, and when do I start picking the labs? That comes down to where you put the zeros in the binary string. Does that make sense? That's it. So what we were doing was 10 plus 4 minus 1 over 4 minus 1. Okay, which is 13 choose 3. Just like we were saying. And that will tell us how many we could have, and why not? We have time. Let's go quickly to Python. I think. Darn. We'll just have to do it ourselves. So 13 choose 3 is going to be, this is important, so we're going to solve it ourselves. Certainly there's a factorial, right? Yeah, cool, that works. That's good enough for me. So 13 choose 3. That is going to be 13 factorial over 3 factorial times 13 minus 3 factorial, so that's 10 factorial. So it looks like it's 286 possible baskets full of puppies. So now that we know that answer, I think we are ready to call it a day. So remember to watch the lab video, and I will see you next week.